This definition is on existential quantifiers and existential statements. Suppose Qx be a predicate and D be the domain of variable x. We can define an existential statement that basically is a statement saying that there exists, there is a value like x in domain D such that the predicate Qx is true. It's true if and only if the predicate Qx is true for at least one value in the domain. It is false if and only if your predicate is false for all x in domain D. So we defined universal statement. This time we are defining an existential statement. It says there exists, there is a value like x in domain D such that your predicate Qx is true. This is called existential quantifier. And we read it as there is, there exists. Let's go over some examples to feel more comfortable about what's happening here. Consider the following statement. It says, there exists a positive integer like m such that m squared is equal to m. So the way that we write this is, there is a positive integer such that with the condition that m squared is equal to m. Is this a true statement? So remember that this is an existential statement. There exists m in domain D, which is positive integers, such that m squared is equal to m. We have an existential statement. Remember that to show that this existential statement is true, you only need to show that it is true for at least one element in the domain. So we're not looking for a value that makes this statement false. We're looking for a value that makes this statement a true statement. Like what? Let's set m to be 1. M belongs to the domain and 1 squared is equal to 1. So we found that unique value, a specific value that makes this a statement a true statement. Let me give you another example. This is part A. So for part B, we have the following statement. Another existential statement. I'm going to check to see if the statement is false or true. So pay attention to the domain. Now the domain is specific values like 5, 6, 7, and 8. There is no other value to be considered. Our domain is limited. Consider the statement, there exists. There is a value in this domain such that m squared is equal to m. So I cannot use 1. 1 is not acceptable. 1 is not in this domain, right? 1 is not in domain E, which is including 5, 6, 7, and 8. It's different from the previous example, right? So what should I do? I need to check each element here. Well, I have 5 in this domain, right? But 5 squared is not 5. What about 6? 6 belongs to this domain, but 6 squared is not 6. What about the next element? 7 is in domain, but 7 squared is not 7. And the last element is 8. 8 is in the domain, but 8 squared is not equal to 8. So what's the meaning of that? It means that this statement is false. This existential statement is false, right? So again, do not confuse universal statement and existential statement. There's a difference between them. For universal statement, we have for every, for any. For example, in this case, m in positive integers, m squared is equal to m. There exists a value like m in positive integer set such that m squared is equal to m. So take a look. Compare these two. The very first one is universal statement and the second one is existential statement. This is just a note for you, right? The first statement says for any positive integers, m squared is equal to m. This is a false statement. But here it says there exists a one value that m squared is equal to m. This is a true statement. So know the difference between these two so you don't get confused when it comes to universal statement and existential statement. Let's move on to more practice. In this example, I'm going to rewrite the following formal statements in a variety of equivalent form. And it says do not use universal quantifier or existential quantifier. So again, remember that this symbol is called universal quantifier. It says for any, for all, for every, and so on. This symbol is existential quantifier. It says there is, there exists, and so on. Very well. This statement is basically a universal statement. It says for every real value, if you raise it to power 2, it's going to be more than or equal to 0. Okay, let's write this down for you. Make sure we have enough space for the rest of them. So for A, we can write it this way. We can say that all real numbers have non-negative squares. All real numbers have non-negative squares. We can write this in other form. Every real number has a non-negative square. Any real number has a non-negative square, and so on. Let's take a look at another example for you. It says for any real number, its square cannot be -1. All real numbers have squares that are not equal to -1. Or you can write it this way. You can say no real numbers have squares equal to -1. No real number has a square equal to -1. Let's take a look at another example. There is a positive integer such that its squares is equal to itself. You can write it this way. Some positive integers equal their own squares. So there are different ways to rewrite these statements in English. As you can see, for the first one, I used all. For the second one, I used no real number. Let's take a look at more examples. Rewrite the following statement so that quantifiers trails the rest of the sentence. What do we have here? For any integers like n, 2n is even. We can write it this way, so pay attention. 2n is even for any integer like n. Another example for you. Here we have there exists at least one real number like x such that x squared is less than or equal to 0. We can write it this way. X squared is less than or equal to 0 for at least one real number x. For at least one real number like x. Let's move on to more examples for you. Rewrite the following statement informally without quantifiers or variables. It says for every x in R or for any real value, if x is more than 2, then x squared is more than 4. One quick note for you. When you have conditional statements, you always use universal quantifier. So just a quick note, P then Q is a universal statement. Very well. So we can write it this way. We can say that if you have a real number, if a real number like x is greater than 2, is greater than 2, then basically its square is more than 4. Is greater than 4. You can take a look at this algebraically as well, right? You can verify this statement using algebra. So if you're interested in going back to algebra, if I ask you, for example, to visualize f of x equals to x squared minus 4, I'm going to check the domain where x squared minus 4 is more than 0. So let us go back to the algebra and visualize this quadratic function. X passes at 2 and negative 2. When you set this equal to 0, x is plus minus 2. And then if you plug in 0, you get a negative 4. So you can visualize this quadratic function this way. Correct? Let me just make sure you have a straight line here. Okay, perfect. So we're looking for the domain where x squared minus 4 is more than 0. This guy is x squared minus 4. But it is more than 0 when your y value is more than 0, right? This portion says, hey, the y value is more than 0. But the y value is nothing but x squared minus 4. So basically, you're going to ignore everything down here. So take a look at the domain. For the domain, x is more than 2. x is more than -2. So if x is more than 2, well, basically we can see x squared is more than 4, or x squared minus 4 is positive. So algebraically, you can verify that as well. Whenever you get stuck, you can take a look at the algebra behind this and try your best to analyze the statement as well. Perfect. Let's see what's next.